Hello students, welcome to this module number 5, other materials and material selection. Here we are going to discuss about processing of plastic. In that, first one is calendering, another one is thermoforming. So let us discuss about the calendering. Okay, what do you mean by calendering? This calendering is a continuous process for producing a high volume of and high quality plastic film like PVC sheets or belt conveyors, etc. Okay, as we have seen this figure, there is a process makes use of four heated rollers. Okay, and at different size and rotating at different speed and temperatures and directions. So the plastic material, there is a fed stock in the form of a powder, and it including a necessary additive to is fed into the roller. So where it is heated and melted, then the shaped into a sheet. Okay, and this product is going then cooled by passing through this cooling roller, and then maybe rolled up desired. And this gap is going to be between heated roller influence the thickness of production. So while this temperature and speed of the roller influence the luster and finish of this product. Okay, so here in this figure you can see that is the first part we call it as that is this one is heated rollers, and this one we call it as plastic material, that is where it is going to be called as feedstock. And this one is what that is plastic sheets, it is coming out from this process. And these bottom are somewhere here, it will be one more roller will be there, that will be help for cooling the plastic, that is cold rollers. Okay, and for this second one is what we call heated and formed sheets. So that is going to be taken in between these two rollers, this is heated rollers. So this is about the calendering, and let us understand by detail by seeing the industrial video for this process. Okay.
Once again, the very beginning of mixing and turning and milling the PVC. You keep on milling it until it gets to the right gauge and the right temperature. All the air becomes out of it. Here's another close-up of the calendar. That's the thin ribbon of PVC that's fed through. It gets completely smashed through these heavy-duty pressurized rollers into that film. Comes back down here into the width that's been desired. This is all trim right here. And then gets spun back through the machine where it's going to meet the backing. Now this is the back side of the calendar, so you can see at the top the ribbon comes down, it gets spread into a film, which is right there, and then it gets fused right back onto the backing, which is this white thing coming through. The backing and the PVC get fused together through the calendaring process. So the third stage is then basically, as it got fused over there together, those were the two parts where they met. Here comes the clean sheet of PVC vinyl, and it gets cooled down through these cooling rollers and gets wound up through the backside here. And then after this, it'll go to this next station, which is the embossing station.
I hope you understood this by seeing this video of this process, and let us move with the next slide, that is thermoforming. Okay, what is meant by thermoforming? So this thermoforming makes use of applications that heat and differential pressure for forming the plastic sheets into the desired shape. So here in this figure you can see that one of the thermoforming setup. so it shows the various thermoforming processes are there. So we can in available in the industry there are vacuum type and pressure type of thermoforming will be there. This is general mechanical thermoforming. So for the vacuum thermoforming, in which the plastic sheet is going to be clamped to a frame and it is uniformly heated to make it soft and flowable. But in this vacuum is then applied through the small holes in the die, which is positioned below the frame. So this sagging plastic sheet is rapidly pulled against the die, causing the sheets to conform to the shape of die or mold. Okay, and another type of also it is available, that is a pressure type of thermoforming. It is an improvement of overcome the vacuum forming, in that it is utilized to both vacuum and compressed air to the force the plastic sheet against the die or mold. And vacuum pulls one on one side, the sheet is going to be compressed. Compressed air pushes on the other side, it causing the sheets is conformed to the shape of die or mold. Okay, so in this figure we can see that is thermoforming is used to make the products like jelly container in restaurants, refrigerator inner panels, and container or trays or packing units or drinking cups and food packing and similar such kind of parts. Okay, so here one is the force, that is vacuum, the pressure based thermoforming. Another one is vacuum. Okay, so these both figures we can observe in this figure. So for better understand, we can see one of the video related to this thermoforming. Let us look at once.
Forming methods have 6 processing steps. They are load, heat, form, cool, part removal, and trim. Load. The sheet is placed in a clamp frame and held down on all 4 sides. Heating. After loading, the sheet is ready to be indexed to the heating station. Depending on the machine design, the sheet will be indexed to the heaters or the heaters move to the sheet. In either case, heaters above and below the sheet heat the plastic to its forming temperature, typically from 285 degrees to 375 degrees Fahrenheit, depending on the type of plastic. As the sheet is heated, it loses strength and begins to sag. To experienced thermoforming personnel, the amount of sag and the shape of the sag is a useful indicator of how evenly the sheet has been heated and how well the plastic can be formed. For some part designs, the sheet is intentionally heated unevenly to improve the plastic distribution in the formed part. Molds for production are usually made of aluminum. Aluminum is easy to machine from a solid block or be cast from a pattern. Aluminum is an excellent conductor of heat, so it cools the plastic parts efficiently. Prototype molds and molds for low production quantities might be made out of wood, fiberglass, and even plaster. When the sheet is sealed against a mold surface, air under the sheet is trapped. Using a vacuum to remove the air forces the sheet against the mold surface. The air under the sheet leaves the mold through vents. To remove large amounts of air, the mold has gaps in the assembly. Drilled vent holes are used in locations where small volumes of air are likely to be trapped. Here is the simplest of the thermoforming methods. The plastic sheet is heated in a clamp frame until it's rubbery. A vacuum removes the air from under the sheet, and atmospheric air pressure stretches the sheet into the mold. Some regions stretch more than others, and this causes uneven sheet thickness. In this part, made in a female mold, The thickest plastic is at the top flange, where the sheet first touches the mold surface and begins cooling. The sheet becomes thinner as it was stretched to the bottom of the cavity. The distribution of the sheet in this female mold is thickest at the top flange, thinning down along the walls, and the thinnest at the base of the molded part. If we form the part on a male mold, the mold moves up to the heated sheet. The plastic first touches the metal at the projection, and this plastic is held there and begins cooling. The rest of the sheet thins as it is stretched to the flanged region. The sheet is sealed around the mold and vacuum is applied. Atmospheric pressure presses the sheet onto the mold. The sheet distribution is the opposite of the previous mold, thick at the base of the formed part and a decreasing sidewall thickness towards the flange. The flange itself will have varying thickness, thin at the corners, thicker towards the clamp frame. Drape thermoforming is where plastic sheet is draped over a male mold. The sheet stretches as it is pulled. Another way to stretch the sheet into a deep section is called plug assist. In fixed plug assist, a plug is attached to the upper half of the mold. The mold closes and the plug stretches the sheet. A vacuum then pulls the sheet onto the surface of the mold. The plug has pre-stretched additional plastic where it is needed. The shape of the plug affects the sheet distribution to improve the part thickness along the bottom and in the corners. A variation of plug assist is third motion plug assist, where the plug moves into the sheet after the mold is closed. A basic thermoforming causes the sheet to be thinnest where the plastic sheet is stretched the most. There is very little control over part thickness. Plug assist and drape assist are methods to improve the sheet thickness distribution in thermoformed parts. In this example of plug assist, a plug moves into the sheet. Until the vacuum is started, air trapped under the sheet causes the plastic to billow and begin to climb up the sides of the plug. The plug should not cool the plastic and may even be temperature controlled. The plastic next to the plug keeps its thickness, but the plastic not in contact with the plug continues to stretch and thin. When the vacuum is applied by either a timer or a position sensor, the sheet is pulled away from the plug and onto the cavity walls, where it cools quickly. It's apparent that sheet distribution is affected by how far the plastic climbs the plug before the vacuum pulls it away.
I hope you understood this video or concept. So some of the other processing of plastic we'll discuss in the next video. Thank you.